Hello friends. So today we are going to solve total of 5 questions, and they were asked in the year 2000 and in the year 2011, and we have 2009, and we have a 2015 mains paper question rather, and the last one is 2013. So in the first question, which was asked in the year 2011, and it is given as a series RC circuit is connected to AC voltage source, considering two cases: when C is without a dielectric medium and when C is filled with a dielectric constant of 4. The current IR through the resistor and voltage VC across the capacitor are compared. In the two cases, which of the following is or are true? So this can be a multi-correct option question also. And in the question, it is given as a simple RC circuit. So we can just draw a rough approximate diagram for it. We have a resistance and capacitor, and it is connected to AC source, capacitor. And from here, the two cases are derived. In the first case, it is given that the capacitor is without dielectric, so we can consider that it is having a dielectric constant of 1. In the second case, it is said the dielectric constant is 4, so we can say value of K is equal to 4. And we are supposed to find out the relationship between the current in the two cases, case A and case B, as well as the voltage across the capacitor in case A as well as case B. So we have two cases. So in case A, capacitor has no dielectric. Capacitor has no dielectric, so we can say value of K is 1. And then we have case B, and it is given the capacitor has a dielectric. Has a dielectric with a constant of K as 4. And the quantities which we are going to compare is our two things. One is the current and another one is the capacitor voltage across the capacitor. So first of all, let us try to find out what will be the capacitance in both cases. Capacitance in both cases. For case A, which is without dielectric, we can say capacitance of A is equal to C, and where this C is capacitance without dielectric. C is capacitance without dielectric. For case B, CB is K times CA. Dielectric constant is given as 4, so this comes as 4 times C. Now we are going to find out the impedance of RC circuit. impedance of RC circuit. And first of all, we find out reactance, that is XC, which will be equal to 1 upon omega C, and we can divide it into two cases. For case A, we can see XCA will be equal to 1 upon omega C, and for case B, XCB will be equal to 1 upon omega 4C, which can be written as 1 upon 4 omega C, and this comes as XCA divided by 4. And we know that the total impedance of the series RC circuit, that is Z, is given as R square plus XC square ka square root. And once again we divide into two cases. We have case A. For ZA will be equal to R square plus 1 upon omega C, its whole square and square root. And then we have case B. And case B is our ZB, which will be equal to R square plus 1 upon 4 omega C and its whole square root. We can just solve it a little bit. We can write it R square plus 1 upon 16 omega C whole square and its square root. So if we compare the impedance, we can clearly understand that the value of comparing impedances so value of R will be same in both cases, but if we compare the reactance of capacitor in case A and case B, we can clearly understand that 1 upon 16 omega C whole square will be less than 1 upon omega C square. So from this we can say that our ZB will be less than our ZA. And if the current through the resistor is given as IR, current through the resistor, if given as IR, then we can write a general formula for this, that our IR will be equal to Vrms divided by Z. Now once again we divide into two cases. For case A, we can write our IRA will be equal to Vrms divided by the impedance which we just calculated, R square 1 upon omega C whole square and its square root. Similarly, we can write for case B is our IRB, which will be equal to Vrms divided by, this comes as R square plus 1 upon 16 omega C whole square and its square root. Now we make a comparison, and we've already found out that impedance of ZB, case B, will be less than for ZA. Making comparison, ZB is less than ZA, and keeping in mind these both the terms are in denominator. So therefore we can say our current in case B will be greater than current in case A. Now we can find out the voltage across the capacitor. Voltage across capacitor, and which we can see is our VC is equal to I multiplied by XC, and we already know the value of current in both cases. So let us revise this formula. For case A, we can write this as for VCA will be equal to our IA multiplied by XCA, and for case B we can write a VCB is equal to IB, and this comes as XCB. We already know our IA will be nothing but our IRA, both are same. So this becomes IA is equal to our VRMS divided by R square plus 1 upon omega C whole square and its square root, and our XCA will be equal to 1 upon omega C. So therefore we can say that our VCA will be equal to the product which comes as VRMS divided by R square plus 1 upon omega C whole square its square root multiplied by 1 upon omega C. Similarly, we can write for case B. Case B, we can write that VCB is equal to VRMS divided by R square plus 16 omega C whole square square root multiplied by 1 upon 4 omega C. Now we are going to compare our VCA and VCB. Comparing VCA and VCB at we already know that our IB is greater than IA. IRB is greater than IA. Okay. So this we can simply say IRB is greater than our IRA. So keeping in mind that our RRB is equal to our IB and our RIA is equal to IA. And our XCB will be also equal to XCA divided by 4, which we already found out. Okay. So therefore, the ratio VCB upon VCA will be equal to IB multiplied by XCB divided by IA multiplied by XCA. And the ratio of XCB upon XCA is our, from here we can say our XCB upon XCA is equal to 1 by 4. So this can be written as IB upon IA multiplied by 1 by 4. And we already know the ratio of IB and IA can be calculated by using the impedance equation. So we can say that our IB upon IA will be equal to ZA upon ZB, which comes up R square plus 1 upon omega C whole square divided by R square plus 1 upon 16 omega C whole square, and both are in square root. So we can just simplify it, and we assume that let x is equal to 1 upon omega C. Therefore, our ZA comes as R square plus x square square root, and our ZB comes as R square plus x upon 4 whole square and its square root. So substituting the respective values, we get the ratio IB upon IA is equal to R square plus x square and its square root, and divide by R square plus x square upon 16. And from here we can also say that our VCB upon VCA will be equal to 1 upon 4, and we can write it a combined square root. This comes as R square plus x square and R square plus x square by 16. So obviously we are mainly interested in denominators, that is going to sort out. So we can say that our denominator R square plus x square by 16 is less than our R square plus x square. So it means this gives us that VCB is less than our VCA. Okay. So final answer with respect to current is our IRB is greater than IRA, and we have VCB is less than VCA. So the option that is, we have our IRB is greater than IRA. So option number B is correct. IRB is greater than IRA, and we have VCB is greater than VCA. So option number B and D are correct. Option B and D are correct. Next question, which was asked in the year 2009, and it states that two metal rings A and B, identical in shape and size but having different resistivities rho A and rho B, are kept on the top of two identical solenoids as shown in figure. When the current I is switched on in both the solenoids in identical manner, the ring A and ring B jumps height HA and HB respectively, with HA greater than HB. The possible relationship between their resistivities and their masses MA and MB is or are. So this is also a multi-correct option. So in the figure we have two metal rings A and B, and they have different resistivities. So we have resistivity here is rho A, and here we have resistivity of rho B, and rest everything is identical. Current is given to same, and they jump height HA and HB. So height jumped by A is our HA, and jumped by B is our HB, where HA is greater than HB. So we are going to focus mainly on this condition, that our HA and HB, and based on this we are going to find out the relationship between the resistivities as well as their mass. So first of all, we try to understand the, you can say, because it is placed on a solenoid, and as soon as the current in the solenoid is changed, the magnetic flux through the ring changes and the EMF is induced in the ring. So we start from there only. We say induced EMF and current. Induced EMF and current. So when the current in the solenoid is turned on, magnetic flux through the ring changes. Magnetic flux through ring changes, and because of this, inducing an EMF in the ring. Inducing EMF in the ring, and this induced EMF, that is our E, is our minus d phi upon dt, and phi is our flux. So also we know that the flux phi is equal to B and A, where A is the area of the ring and B is the magnetic field, and there will be induced current in the ring. So we can say that induced current I induced will be equal to EMF divided by R, where R is the resistance of the ring. So in this case we can say that our B is the magnetic field, A is the area of ring, and our R is the resistance of the ring. Resistance of the ring, and we can write the resistance R will be equal to rho L upon A, where rho is the resistivity and L is the length. Rho is our resistivity and L is the length. And here let me write this A as area of cross section. Okay, that will make it more clear. Here our AC is area of cross section. So if it is given that the ring is identical, therefore identical in shape and size, therefore value of L as well as AC will be same in both the rings. So it is given rings are identical in shape and size. Shape and size. So which means L, that's the length, and AC, that's the area of cross section, this will be same for both rings. So therefore we can write that our resistance is directly proportional to the resistivity. Now we can find out, because of the induced current which is going to interact with the magnetic field and resulting in a force will be produced that is going to cause the ring to jump. So we can say that the force on the ring, so we say induced current which we represented as I and D interact with the magnetic field, interacts with magnetic field to produce a force, F that causes ring to jump, and we can call that a Lorentz force also. And the force F is directly proportional to induced current and our magnetic field, and our induced current is inversely proportional to the resistance, which will be inversely proportional to resistivity. So we can say magnetic field, that is B, is same because current is same for both rings. So as a result, we can say our force is directly proportional to induced current and inversely proportional to the resistance, and we can say inversely proportional to the resistivity. So basically it means that lower the resistivity, higher will the force. You can see from here that lower is the resistivity, greater is force. Now, because they are going to jump, so we can find out the relationship between the kinetic energy as well as height. We say kinetic energy and height. So if we say that work done by the force F over a small distance delta Z, which will be converted into the kinetic energy. So work done will be equal to half mv square, and work done will be equal to force into delta Z. So force into delta Z will be equal to half mv square. So you can see work done by the force F over a small distance small distance delta z converts to kinetic energy. Converts to kinetic energy. So we can write our F into delta Z will be equal to F into delta Z will be equal to half mv square. And at maximum height, this kinetic energy will be converted into potential energy. At maximum height, kinetic energy is equal to our potential energy. So we can write our half mv square is equal to mgh. And from here we can say that our h is proportional to force oblique mass and indirect proportional to 1 upon resistivity multiplied by mass. And we are given that HA is greater than HB. This is given to us. Therefore, we can divide this equation number 1 into two parts. So you can say from equation 1, we can write our HA upon HB is equal to 1 upon rho A MA divided by rho B, 1 upon rho B divided by rho MB. This gives us that rho B MB is greater than rho A upon MA and greater than 1. So we can write further that our rho B MB is greater than rho A MA. Now all the options that are given to us should be able to satisfy this particular solution. Okay. So let us start one by one with option A. We have option A that is given as that rho A is greater than rho B and MA is equal to MB. Now it is given that MA is equal to MB. So let us write this as equation number 2. So we can say using equation 2, and if we substitute that we are given rho A is equal to rho B and MA is equal to MB, and if you make a comparison from equation 2, this solution option A is incorrect. Option A is incorrect because if we substitute MA is equal to MB in equation number 2, we get this as rho B is greater than rho A, but here it is given reverse. So option A is incorrect. Now let us check option B. Option B gives that rho A is less than rho B, and we have here MA is equal to MB. So once again, using equation 2, using equation 2, if you substitute here MA equal MB in equation 2, and MA and MB will cancel, so we are going to get this particular condition. Okay, so we can say option B is correct. Option B is correct. Now let us come to option C. And option C states that our row A is greater than row B, and we have our MA is greater than MB. So once again, using equation 2, it is given that row A is greater than row B and MA is greater than MB. So from here, we can clearly understand that the product of row A, MA will be greater than row B and MB, which is in contradiction with the given condition. So option C is incorrect. And we have last option, that is option D. And it is said that row A is less than row B and MA is less than MB. And from here we can clearly see that this option is correct. Option D is correct. So we have only two options that are correct, and the option is D is correct and option B is correct. So we have that option B is correct, and we have option D is correct. Option B and D are correct. Now we come to the next question, and the next question was asked in the year 2050 mains. And here it is said that an LCR circuit is equivalent to the damped pendulum. In the LCR circuit, the capacitor is charged to Q0, then connected to L and R as shown. If the student plots the square of the maximum charge Q square max on the capacitor with time t for two different values of L1 and L2. L1 is greater than L2 of L. Then which of the following represents this graph correctly? The schematic and not drawn to the scale. In this case, we are given a LCR circuit, and it's said to be that it is equivalent to a damped pendulum, and capacitor is charged to Q0 and then is connected to L and R. And student plot the square of maximum charge for two values of inductor. One is our L1, the other one is L2, where L1 is greater than L2. So we have to identify the variation of this square root of maximum charge, square of maximum charge with respect to time t. Basically, we are going to find out the decay rate of the charge. And it is mentioned that it is a damped pendulum because of the presence of this particular resistance. The oscillations are continuously going to die because of the energy that is consumed by this resistance R. Therefore, the charge Q is going to follow a damped exponential decay. You can say LCR is analogous to damped pendulum and therefore the charge on capacitor follows a exponential decay, damped exponential decay, damped exponential decay. So we can write the equation that our max T will be equal to our Q naught e raised to power minus R upon so e raised to power minus RT upon 2L. Now if you square both sides, because we are interested in the square of this maximum current, maximum charge, this is squaring both sides, we can write we get this as Q square max will be equal to Q naught square e raised to power minus R upon L multiplied by T. Now from this equation we can clearly understand that the value of resistance in both the cases is same, whereas this value of inductor in first case is L1 and in second case is L2. So the decay rate will be determined by the ratio of R upon L1 as well as R upon L2. So we can write the effect of inductors on decay rate. So the decay rate of the charge, that is square of charge, decay rate of the square of charge is determined by R upon L, and we are given that our L1 is greater than L2. So from here R upon L1 is less than R upon L2. So it means the damping is slower for larger L. We can say damping is slower for larger value of L. So from here we can just make an approximate that obviously there won't be option A as well as option B. Option A, it says that is same for L1 L2, which is just we concluded that the decay will be different, and in the second case it said that the L1 is higher side, so here it is L2 is the higher side. So only option that are left are option C and option D. In both the cases the L1 is on the higher side. So we have to find out which of them is the correct one. Now from the equation, if we see the equation of the this charge, we can see there is exponential function, and because of this exponential function, the graph will be following a exponential. Okay, so option number C is just with a straight line, so this will be also incorrect. So the only option correct is option number D. So we can say that damping is slower for large R, therefore the curve of L1 lies above the curve for L2, and we can also say that because of the exponential function, in equation 1, so let us call this as equation 1, the decay will be exponential. The decay will be exponential in nature. So therefore option D is correct. Next we have question which was asked in the year 2000, and it says that a coil of wire having a finite inductance and resistance has a conductor ring placed coaxially within it. The coil is connected to a battery at time t is equal to 0, that a time dependent current I of t starts flowing through the coil rather. If I2 is the current induced in the ring, Bt is the magnetic field at the axis of the coil due to I1t, then as a function of time t greater than 0, the product of I2 and Bt will be. So here we have to find out what will be the nature of this product I2 and Bt. So we are given that we have a coil which is having a finite inductance as well as resistance. So the finite inductance, let us suppose, is given as L, and the resistance is given as R, and they are connected to a battery at time t is equal to 0. And it also says that we have a conducting ring is placed coaxially within it. So we say that coil which is having a finite inductance L, and it is having a finite resistance R, and they are connected to battery at t is equal to 0. Connected to battery at t is equal to 0. Therefore, there will be time dependent current which is given as I of t, I1 rather, in the coil. So this results in a time dependent current which is given as I1t in the coil. and it is also said that a conducting ring is placed coaxially inside the coil. Inside the conducting ring is placed coaxially inside the coil. Inside the coil. And because of the current I1t, let us suppose it produces a magnetic field B of t at the axis of the coil. So we say this I of t produces magnetic field B of t at the axis of the coil. Axis of coil. And because of this magnetic field B of t, it is going to, because it is also dependent upon t, it means changing the time, it is going to induce an EMF in the ring, and this EMF in the ring will generate a current that is I of 2 in the ring. Okay, that will be obviously in the opposite direction, so that it opposes the change of B of t. So you can say that B of t changes with time, inducing EMF in the ring. And because of this induced EMF generates a current which we call as I2 of t in the ring. And this induced current will oppose the change in B of t, which opposes change in B of t. So we have to find out the product of this I2 of t as well as the Bt at time greater than 0. So let us first of all make a analysis of the magnetic field due to coil, which is our B of t. Magnetic field due to coil. And along the axis, we know that the magnetic field is proportional to the current. So magnetic field due to coil at the axis is proportional to current. So we can write that our B of t is equal to K I1 t. Here we have assumed K is the proportionality constant. K is our proportionality constant. And it is said that both it has inductor as well as capacitance. Therefore, we can write the equation of the current. Because this is simple RL circuit, or RL circuit, the current equation is, and the current is given as I1t. So we can say I1t is equal to I naught 1 minus E minus T upon tau, where I naught is a steady state current given as V upon R, tau is our time constant, this will be given as L upon R. So therefore, the magnetic field, we substitute value of current, we get that V of t will be equal to K times I naught 1 minus E minus T upon tau. Now we are going to find out the induced EMF. Induced EMF, let us suppose that is given as E of 2, which will be minus d phi upon dt, and flux is our, phi is our flux, which is equal to B multiplied by A. So our flux phi is B times A, where A is the area of the ring. Area of the ring. We substitute the value, we get our induced EMF is minus A dB upon dt, because it is given that magnetic field is changing with the time. Now here we can substitute value of B, and this comes as minus A d of dt, and here we have our B is our K I naught 1 minus E, and this is minus T upon tau, and K I naught is nothing but our constant factor. So we can write our induced EMF E2, it will be coming as K AK, and here we have I naught e raised to power minus T upon tau, and this whole factor divided by tau. Therefore, the induced current I2, which is in the ring, we can say that our induced current in ring, which is our I2t, will be equal to induced EMF divided by resistance, where R2 is the resistance of the ring. R2 is our resistance of ring. Therefore, we substitute the value of our induced EMF, we just calculated it. So we get I2t is equal to E2 upon R2, and which comes as AK I naught divided by R2 times tau, and this is e raised to power minus T upon tau. And we need to find out the product. We found our I2, and we have also calculated our B of t. So we are interested in product. So we can say that product of I2t and times Bt. We simply substitute the respective equations. We can write that this will be equal to a k I naught divided by R2 tau e raised to power minus t upon tau times k I naught 1 minus e minus t upon tau. And we can just make a minor adjustment here. You can see this product will be coming as a, this comes as k square I naught square divided by R2 tau and comes as e raised to power minus t upon tau 1 minus e minus t upon tau. So it is given that this function for t is equal to 0, and we are going to find out that t is equal to infinity. You can say at t equal to 0, the product, you can easily understand this will be giving us 0 because e raised to power 0 will be our 1 and this is 1 minus 1, so this will be 0. So therefore from here we can say I to t multiplied by bt is equal to 0. And second, we can write that at t tends to infinity, this function is also approaching 0. Also approaches 0. So it means it is going to reach a maximum value at some intermediate time. So from here we can say it reaches a maximum at some intermediate time. Intermediate time. So therefore the product I to t times bt increases, first increases, then reaches the peak, reaches a peak and then decreases, then decreases back to 0. And this happens as time progresses. As time progresses. So let's check which option is the correct one. So it does not increases continuously with time, it does not decrease continuously with time, it varies with time, so this option is also incorrect. So only option correct, it passes through a maximum value. Okay, so you can say option number D is correct. Option D is correct. And this is our last one. It was asked in the 2015 main. This was asked on 2015 mains. And we are given that a metallic rod of length L is tied to a string of length 2L and is made to rotate with angular speed omega on a horizontal table with one end of the string fixed. If there is a vertical magnetic field B in the region the EMF induced across the ends of the rod is. So with this is our figure. We have a table, and on table there is a rod of length L, and we have a string whose length is given as 2L, rotated in the presence of magnetic field, which is given as B, and it is said that magnetic field is vertical. So magnetic field will be something like this. And we have to find out the EMF induced across its terminal as it is going to rotate in this magnetic field B. So it is given that this rod is rotating in a you can see with the angular velocity of omega. Okay. So if we can write that the motion of the rod and from here we can also see that its length is L. So at any particular instant, the one end of this rod from the center will be at a distance of 2L, and the other end will be at a distance of 3L. Okay. And we can say that the distance of any point on the rod from the center from the distance of any point on the rod from the center of rotation varies from 2L to 3L. And we can find out it is rotating with angular velocity omega. So we can say that for any point on the rod which is at a distance r from the center, the linear velocity v will be equal to r omega. You can say the linear velocity at any point on the rod at a distance r from the center of the rotation if given as v, then v will be equal to r multiplied by omega. And if we consider, this is our rod and this is our fixed point. So this is our 2L and this length is given as L, and we have considered that the linear velocity at a distance any point, and here let us consider a small portion of the rod which is dr. So we can write that the motional EMF for dr, let us suppose that is given as dE will be equal to bV multiplied by dr. We already know is our r omega, so we substitute it, we get this as b r omega multiplied by dr, and this r varies from 2L to 3L because this point is 2L and this point is 3L, not R. So you can say that our R varies from 2L to 3L. Therefore, the total EMF will be equal to B omega integration 2L to 3L, and here we have R dr. This can be written as B omega, and here we have our R square, and this is from 2L to 3L. And now it is a simple calculations. We get induced EMF E will be equal to B omega, and this comes as 3L square, which comes as 9L square. Sorry, here has to be 2 minus this comes as 4L square divided by 2, and this comes as B omega, and we have a 5L square upon 2. So the induced EMF will be equal to 5/2 B omega L square. So the option number D is the correct option. Option D is correct. I think this completes all the questions. Yeah, so these were all the questions which were asked in the year 2000, 2011, 2009, 2015 mains and 2013. So this complete all the questions. Thank you.